In our previous lecture, we introduced the second law of thermodynamics for both open and closed systems, and we solved a couple of very simple examples. And now in this lecture, we're going to step it up just a little bit and apply the second law to a couple, or at least one system that we've already looked at before, and then a couple of new systems, and to see if we can learn a little bit more about approaching problems that involve entropy and entropy balance. So the first example that we're going to solve today is that a simple diatomic ideal gas is compressed rapidly, which often means two things. One is irreversibly, because if you think about it, some of these irreversibilities, like friction, are going to be much more severe when you try to do something quickly as opposed to when you try to do something slowly. The other thing that happens when you do things fast is that heat transfer may not have time to occur. So rapidly is sort of code for irreversible and adiabatic. So we're going to compress this gas irreversibly, though adiabatically, from 1 atmosphere and 25 degrees C to 10 atmospheres and a final temperature of 344 degrees C. And the problem asks us to do a couple of things. The first one is to show that the process doesn't break the second law. And the second part is to determine how much hotter the gas would have been than if the process had been done reversibly. Because remember, these irreversibilities result in the evolution of heat. And that, of course, is going to heat up the gas more than you might have expected, or the final temperature should be hotter than it would have been had you done this reversibly. So let's do the first part where we ask ourselves, does this obey the second law? And then we'll do the second part and we'll think about what would have happened if this would have been done reversibly. Now, of course, when we ask a question about obeying the second law, we're asking a very simple question, and that is, does the generated entropy have a value that's greater than or equal to 0? Because, of course, we know that any process must have SG greater than or equal to 0. And to figure this out, let's go right to the energy balance. Of course, we have our closed system energy balance is that the generated entropy is equal to delta S for the system minus Q over T surroundings. Now, in this particular case, we know that our process is going to be adiabatic. So if that term is equal to 0, that tells us that the generated entropy is just going to be equal to delta S of the system. And we derived an equation in the last lecture that will allow us to assess this for this simple ideal gas as a function of temperature and pressure. And that was that the change of entropy of our system divided by R was equal to the integral from the initial temperature to the final temperature of Cp over R dt over T minus the natural log of P divided by P0. And of course, in our case, the heat capacity for a diatomic simple ideal gas is just 7/2 times R. So this becomes delta S over R equals the integral from T1 to T2 of 7/2 R divided by R, which of course is just 7/2, dt over T minus the natural log of P over P0. And if we take that integral with regards to temperature, we get that the change in the entropy divided by R is equal to 7/2 times the natural log of T2 over T1 minus the natural log of, and if I'll be a little consistent here with the units, I apologize, right? That's P2 divided by P1. So we have enough information to solve this problem. So delta S over R then equals 7/2 times the natural log of the temperatures in Kelvin, which then is 344 plus 273.15 divided by 25 plus 273.15 minus the natural log of 10 divided by 1. And so we can find then that delta S over R is equal to 0.244. And you would expect this number to be dimensionless because entropy has the same units as R, and this allows us to manipulate the units any way that we want. And so then delta S equals R times 0.244 0.244, so 0.244 times our chosen units, and we're asked in joules per mole Kelvin. So this is 8.314 joules per mole Kelvin. And so the change in the entropy of our system, which was also equal to the generated entropy, is then 2.03 joules per mole Kelvin. And because the generated entropy is greater than or equal to 0, then we can answer this question, is that yes, the process obeys the second law of thermodynamics, which is great. So now let's move on to the second part of this problem and answer how much hotter was the gas in this case than it would have been had the process been done reversibly. And because in this case, the generated entropy is equal to delta S, that means when this process is done reversibly, that delta S is equal to 0. And one of the things that you're asked to derive in your homework is that for any adiabatic reversible process, that this is true, that delta S is equal to 0. And if that's true, our equation where we had delta S over R, which equaled the integral from T1 to T2 of Cp over R, dt over T minus the natural log of P2 over P1, well, that's now equal to 0. And so we have this result that 0 equals this integral. Remember, the result was 7/2 times the natural log of T2 over T1. And of course, that's minus the natural log of P2 over P1. And if I just rearrange this a little bit, you get that 7/2 times the natural log of T2 over T1 equals the natural log of P2 divided by P1. And then I'm going to use a property of logs that we've used in previous lectures, where A log B just equals the log of B raised to the A. And then that means that the natural log of T2 over T1 to the 7/2 equals the natural log of P2 over P1. And then if I take the exponent of both sides, you get the T2 over T1 to the 7/2 equals P2 over P1. And then finally, you can solve for T2. So T2 then, of course, equals T1 times P2 over P1 to the 2/7. And so if we do this calculation, when we know that T1 is 298.15 Kelvin times P2 divided by P1, which of course is just 10 over 1 raised to the 2/7. And so we find that the final temperature in this particular case is equal to 575.6 Kelvin, which of course is equal to 302.5 degrees C. And so if we look at this, the temperature that actually came out of the real process was 344 degrees C. And we're asked how much hotter. So the difference in the final temperatures then is 344 minus 302.5 degrees C, which is 41.5 degrees C. So the gas was significantly hotter for the irreversible case than it is, or than it was for the reversible case. Now, the second example that we're going to solve today revolves around a valve. So steam enters a valve at 30 bar and 450 degrees C and leaves at 10 bar. And if the size of the pipe is the same on both sides, we're asked to find the outlet temperature, and we're asked to find if the process is reversible. So let's look at valves a little bit first. So we haven't talked about this in any of our lectures previously, but really the purpose of the valve is to take a high pressure gas and to relieve some of that pressure, right? So we're going to go to very low pressure. And in a system like this, especially when the size of the pipe is the same on both sides, the velocity doesn't really change significantly. Valves tend to be reasonably well insulated, and we don't really perform any work, right? You just sort of set the valve, but you don't make anything spin, you don't add electrical work, you don't have any PV work. So if we're going to look at a system like this that's new to us, often what I'll do is not just look at the entropy balance, but also look at the energy balance as well. And if you look at this and apply the energy balance, well, we still start with d and u dt is equal to q plus w plus the sum of the enthalpy that's entering the system through mass flow minus the sum of the enthalpy that's leaving because of mass flow plus the kinetic energy and potential energy. And I write it that way because we know automatically we're going to get rid of those terms, right? Because the velocity doesn't change, it's horizontal. If we're operating at steady state, the accumulation term on the left goes to zero. And if we're well insulated and we're not doing any work, all of those terms also go to zero. And so the result for the energy balance is that zero equals the sum of the enthalpy entering minus the sum of the enthalpy leaving. And of course, we have a single component, which is steam, which does not undergo any change in composition, and we're operating at steady state. So that means that the mass flow in equals the mass flow out. And H out minus H in is just minus delta H. So we get this result that the energy balance is that zero equals minus m dot delta H. But of course, then you can divide by minus one on both sides and just get that the result for our energy balance is that m dot delta H equals zero, which then of course means that delta H is going to be equal to zero, and there's no change in the enthalpy. Now for an ideal gas, this would mean that there's no change in the temperature, right? But steam does not behave as a real gas. So we have a situation where we're sending a real fluid through the valve and we have a temperature change. Now the act of doing this to the steam is called throttling, and the temperature should also change, and the temperature change that's caused by going from high pressure to low pressure for a real fluid is called the Joule-Thomson effect. And there's a lot of side reading that you can do about the Joule-Thomson effect, as well as a video in the Learn Chemie website, which I have a link for that in our syllabus, and I highly recommend that you use that. So how are we going to solve this problem for a real fluid? Well, fortunately, we have the steam tables at our disposal, and the steam tables have all the information that we're going to need because it has enthalpy information at many, many temperatures and pressures. It also has entropy information, and that's going to help us to understand whether this process is reversible or not. Okay, so let's use the data that's located in the steam tables to actually find what the final temperature is and to find what the entropy is in the initial and final state. And so if we go to the steam tables, let's look at the initial state where we have steam entering the valve at 30 bar and 450 degrees C. So we know that at 450 degrees C and 3,000 kilopascals, right, or 30 bar, that the enthalpy for the steam is equal to 3344.6 kilojoules per kilogram. And we also know that the entropy is equal to 7.0854 kilojoules per kilogram Kelvin. Okay, so that's our initial state. Now our final state, what we need is to find where the enthalpy at 10 bar is equal to this value, because remember, delta H is equal to 0. And if you go in the steam tables and you look at 1,000 kilopascals, what you're going to find is that you don't have a value that is exactly 3344.6, but you do have values that are close. So at 400 degrees C, we'll find that there's an enthalpy value of 3264.4 kilojoules per kilogram and an entropy value of 7.4665 kilojoules per kilogram Kelvin. So this is just a little bit below the enthalpy that we're looking for. And the next data point to the right of that one is at 450 degrees C. And the enthalpy there is 3370.8 kilojoules per kilogram, which of course is just a little bit above the value that we're looking for. And then the entropy value at that temperature and pressure is equal to 7.6190 kilojoules per kilogram Kelvin. So we have a value slightly above and slightly below. And what you need is a methodology where we can interpolate to the value that we need. And that's actually located in our book on the very first page of the steam tables. So they give us a formula to do this interpolation. And the formula is that M equals x2 minus x over x2 minus x1 times M1 plus x minus x1 over x2 minus x1 times M2. Now, it might not be immediately obvious what it is that we're going to do with this equation, but one of the things that I can say at the very beginning is that you should understand that M is really the value we are trying to find. And X, or the X's, are values that we know. And in our particular problem, at the very beginning here, the value we're trying to find is temperature, and the values that we know are enthalpies. And the subscripts here, 1 and 2, denote which case here you're looking at, right? And so we're going to call this one 1, and we're going to call the higher temperature 2. And what that means is that for us to solve this problem and to find the final temperature, we have an equation that the outlet temperature then equals the enthalpy at 2 minus the enthalpy that we're looking for. And we know that value already, right? We said that that was 3344.6 because we have an isenthalpic process, divided by H2 minus H1 times the temperature of 1, which of course, if you look above, would be 400 degrees C. Then that's plus H minus H1 minus H2 minus H1 times T2. And so we can insert all of the known parameters in here and find that the temperature then is equal to H2 is up here, it's 3370.8, minus the enthalpy we're looking for, which again was 3344.6 divided by 3370.8 minus 3264.4 times T1, which is 400, then plus the enthalpy we're looking for, 3344.6 minus 3264.4 divided by 3370.8 minus 3264.4 times the temperature in state 2, which is 450 degrees C. And then we can find that the exhaust temperature is equal to 438 degrees C. Now, one of the interesting things right away is that this is not isothermal, right? We went in at 450 and we're leaving at 438 degrees C. So delta T was 12 degrees. Again, for an ideal gas, that wouldn't be the case because when delta H equals 0, the integral of Cp dt has to be equal to 0. But for a real fluid where the enthalpy also depends on pressure, you'll have some change in the temperature as you go through a valve. And in fact, the temperature should always go down, okay? Now, that doesn't really help us answer the final question. Is the process reversible? So we did find the temperature, but we didn't ask if the process is reversible or not. Now, if we look at our process and look at the closed system entropy balance, which is dNs dt plus the sum of the entropy that's leaving from mass flow minus the entropy that's entering from mass flow minus Q over T surroundings equals Sg. And of course, asking if the process is reversible is exactly the same thing, again, as asking whether Sg is greater than or equal to, or sorry, is whether it's equal to 0. And so if we simplify the open system entropy balance, well, we were told it was adiabatic, and we already used that in the energy balance, and we also know that we're operating at steady state. And so the result of our entropy balance is that m dot delta S is equal to the generated entropy. So the thing that we want to do in this particular problem is to find then delta S. And if delta S is equal to 0, then that means that the process is reversible. And if it's greater than 0, then of course we know that the process is irreversible. And if we ended up calculating that delta S was less than 0, then of course it would be impossible, but we're not going to find that here in this particular problem. So if we need to do this, we need to find delta S. Well, we already have delta S for the initial state, or we already have the entropy for the initial state, which is right here, right? It's 7.0854 kilojoules per kilogram Kelvin. Now what we need to do is to find the entropy of the final state. And to do that, we're going to apply this exact same equation that we have above here that we used for the temperature, except now instead of T's, we're going to have S's. And so in the second interpolation for us, M is going to be equal to the entropy, but still the X's are the enthalpy. So just like before, then the entropy was equal to almost the same formula, where this is going to be H2 minus H minus H divided by H2 minus H1, now times S1, plus H minus H1 divided by H2 minus H1 times S2. And so our entropy then is equal to 3370.8 minus 3344.6 divided by 3370.8 minus 3264.4 times S1. And just scroll back up here, S1 was 7.4665. Then that's plus 3344.6 minus 3264.4 divided by 3370.8 minus 3264.4 times S2. And S2 was 7.6190. And so we can find that the entropy of the final state of our steam was 7.5812 kilojoules per kilogram Kelvin. And so now we can calculate delta S, right, which is the entropy of our final state minus the entropy of the initial state. And that is 7.5812 minus 7.0854. So delta S equals 0.496 kilojoules per kilogram Kelvin. And remember, the result of our entropy balance was up here, that m dot delta S equals Sg. So in order for this process to be reversible, delta S would have to be equal to 0, and it's not. It's greater than 0. And so because of that, we can answer the second question, that no, this is not reversible. Now, the last example that we're going to solve today is one of my favorite kinds of examples. And I guarantee you, anybody who takes a class with me on the second exam where we really deal with entropy, you'll have a problem just like this, where you're told that some inventor comes in and tells you something. Is this possible? Okay. And so this particular problem says that your coworker at Awesome Engineers Incorporated tells you that their team has developed an elaborate demonstration unit that uses 30 kilograms of steam in a sealed vessel to do work. In this process, the state of the steam is changed from 650 degrees C in 20 bar to 375 degrees C in 5 bar, producing 13 megajoules of work and transferring some amount of heat that's not measured to the room at 30 degrees C. Write and simplify the energy and entropy balance and determine whether your coworker's claimed performance is consistent with the second law of thermodynamics. So for the first part of this problem, we're going to do something very similar to what we've done in previous lectures, where we write the energy balance, and based on what we know, we try to simplify terms, and we do the same thing for the entropy balance. Now, our first step here is understanding what the system is. And the system in this case is going to be the steam inside of the sealed vessel. And the second thing is to ask ourselves, is this an open system or a closed system? And because it's sealed, it's a closed system. So let's write the energy balance for a closed system. And that is that the change in the internal energy is equal to Q plus W. And if we look at this problem, we know that the temperature is going to change, so the internal energy has to change. We know that work is done, and so the W can't go away, and we're told that some amount of heat has to leave the system. So actually, we can't simplify this at all. So now if we write down the entropy balance, we know that the generated entropy is equal to delta S for the system minus Q divided by T surroundings. And we're asked here to determine whether it's consistent with the second law of thermodynamics, which really just asks us, is that term, again, greater than or equal to 0? So we can't get rid of that because it's something we're going to calculate. And we know that the entropy of the system is going to change because we do have pretty significant changes in temperature and pressure, or at least we believe it should change. And we know that the process is not adiabatic, so Q over T surroundings doesn't go away. So this is one of those few examples that we'll look at this semester where we can't simplify the energy or the entropy balance at all. So where do we start? Well, we know that we're going to have to calculate delta S at some point, and we also know that we're going to have to calculate Q as well. Now, my preference in this particular problem is to start with the energy balance, learn everything we need to know, and then to go to the entropy balance. But you could actually solve for delta S first, then use the energy balance to solve for Q. That would be completely up to you, and it wouldn't change anything that we're going to do here. Now, if we're going to use the energy balance to solve for Q, that means that Q is equal to delta U minus W. Now, fortunately, we can find delta U even for a gas that doesn't behave as a simple ideal gas like steam, because internal energy information is also available in the steam tables. So we know that the initial state is 650 degrees C and 20 bar. And so if that's the case, we can read that directly from the steam tables. And we know that at that condition, the internal energy is 3379.4 kilojoules per kilogram. And we know that the entropy is equal to 7.8279 kilojoules per kilogram Kelvin. Okay, so now our final state, where we're at 5 bar and 375 degrees C, that's not in the steam tables. but 350 degrees C and 400 degrees C are. So we're going to have to interpolate again. So at 5 bar, we know that for 400 degrees C from the steam tables, that the internal energy is equal to 2963.5, and that the entropy is 7.7948. And of course, if I have a little bit more rigor here and put in the units, right? This is kilojoules per kilogram, and this is kilojoules per kilogram Kelvin. And then at 350 degrees C and 5 bar, that the internal energy is equal to 2883.1 kilojoules per kilogram. And because we're at a lower temperature, we're not surprised that the internal energy is less. And then the entropy is equal to 7.6343 kilojoules per kilogram Kelvin. Now, we can use the equation that we used in the previous problem, and that's absolutely fine. And it's something I really highly recommend that you do in order to feel comfortable interpolating in the steam tables. But that interpolation formula just assumes a straight line. And if we're looking for a data point right between these two, which is 375 degrees C, which we are, we actually can find it just by taking the average of these two values. So at 375 degrees C, the internal energy is equal to the average of those two numbers, which is 2923.3 kilojoules per kilogram, and the entropy is 7.7145 kilojoules per kilogram Kelvin. Okay, so from here, we can calculate the change in the internal energy of our system. And so delta U, right, the change in the specific internal energy, of course, is just the internal energy in the final state minus the initial state. And we just found the internal energy of the final state, so that was 2923.3 kilojoules per kilogram minus the initial value, which was 3379.4 kilojoules per kilogram. So that was minus 456.1 kilojoules per kilogram. But of course, delta U is equal to m dot delta U. And we know, or sorry, not m dot because it doesn't flow, it's just equal to m times delta U. And so we know from the problem that we have a claim at least of 30 kilograms of steam times minus 456.1 kilojoules per kilogram. And so then delta U is equal to minus 13,683 kilojoules. And now we can use the energy balance to find Q, right, which was just delta U minus W. So this is minus 13,683 kilojoules minus the work that was done. And remember, if the system is the steam, it says in the problem statement that we're producing work, or that the steam is doing work on the surroundings. And so the sign is negative, and 13 megajoules is then 13,000 kilojoules. And you can find that the heat given off in this process is minus 683 kilojoules. And now we have everything that we need to move on to the entropy balance, which was simply that the generated entropy equals the change in the entropy of the system minus Q over T surroundings. So delta S of our system is the entropy in the second state minus the entropy of the initial state. And just like the internal energy, right, we can take the entropy value from there. So we know that S2 is 7.7145 kilojoules per kilogram Kelvin, then minus the initial entropy, which was 7.8279 kilojoules per kilogram Kelvin. And so delta S then equals minus 0.11335 kilojoules per kilogram Kelvin. And so we can calculate delta S, right, as M times the specific. So again, that's 30 kilograms times minus 0.11335 kilojoules per kilogram Kelvin. And so if we do this, we find that delta S is equal to minus 3.40 kilojoules per Kelvin. But this doesn't mean automatically that we don't satisfy the second law, because the change of the entropy of the system can be negative, right? The thing that we're really looking for is that the entropy of the universe, which is both of these terms, is greater than or equal to 0. So if that's the case, then we can find the generated entropy as delta S, which is minus 3.40 kilojoules per K, minus the heat that was transferred, which we calculated was minus 683 kilojoules, divided by our temperature in Kelvin. So 30 degrees C is 303.15 Kelvin. And you find that the generated entropy is equal to minus 1.15 kilojoules per K, or per Kelvin, okay? And this final result, where the generated entropy is equal to 0, actually tells us no, that we're not consistent with the second law, and the proposed process is not possible.